Okay, we are recording.
Okay,
Yeah, we're
I'll
good.
start again then. So I'm going to talk about joint work with Daniel Hartman. Only one in, right? Yeah. And this is something like I was thinking about a problem, and then he was reading this paper by Budney and Goodbye, and then a question about some loops of embeddings of circles, and he'd say, well, answer the question for me. And so it's a cute little result that comes out of it. But I will emphasize that everything I'm going to talk about is about the group pi0 of fifth plus or S4. That is the same thing. That means all connected components of the space orientation preserving diffeomorphisms of S4. And it's awkward making statements about this group because this group might be trivial. So anything you say about a trivial group, if it turns out to be trivial, is trivial. So you know, 10 years from now, it's all worthless, or maybe there's something. So I'm going to talk about some subgroups of this group that might be trivial. Okay, so all right. So let me give you a little bit of background. So first of all, just how do you get some diffeomorphisms of how do you describe diffeomorphisms? We have an n-dimensional manifold. So here's what I'm going to describe a way to produce diffeomorphism manifold. It may seem really roundabout, but is kind of in some context sort of universal. Okay, so that's an n-dimensional manifold. So what you can do is first you can choose some other n-dimensional manifold, and you want to and then you're going to build some n plus one dimensional coordism. I'll call it W by attaching some collection of n plus one dimensional handles to n0, 1 cross n. And 1 cross n, and handles to it, and plus one dimensional handles, and you get some new boundary on top, and so that gives so I want to think of W. It's really important to think W is actually built by these handles. It's not like W came first and then I decomposed it somehow. W comes with construction by handles. And so this is a coordism by attaching handles to this, and then the top boundary is, we'll call it prime. And suppose you were lucky and n prime was actually diffeomorphic to the given n that we care about. So another way to say it, I could start with m and work downwards to just something, right? And I want to fix this diffeomorphism. So fix a diffeomorphism. All right. And then when you say attach handles, so that's some information about how to attach the handles. So I'm going to just be a little bit sloppy about what I mean by that information. There are many different ways to encode such information, but I'll just say using attaching data. Alpha, it depends on what the handles are and so forth. How you but they're basically embeddings of two different neighborhoods of spheres. And then I want to say, okay, here I've got this attaching data. Now let me start fiddling with that attaching data. So 2 is extend alpha. Attaching data to a loop of attaching data.
Excuse me, what was alpha?
Alpha is a vague notion of it's a general notion of attaching data for some handles. So I'm not being very precise because it depends on the context, right? But it's basically frame lengths or whatever.
Okay.
Loop of attaching data. Alpha sub t. So alpha sub 0 equals alpha 1 equals alpha and then it moves around. And in full generality, maybe there's even handle slides. So maybe at some intermediate times it's sort of more complicated, but it's just you move handles around, you do something, starting and ending with that giving handle attaching data. But the point is, you build this cobordism W by starting with alpha, and then you start changing it. Then at all time you get you get your cobordism changes, but it's always diffeomorphic to the first cobordism. Okay, the cobordism anyway. So this gives sort of a loop of cobordisms W sub t, and because each because I'm always attaching to the bottom, so this is a cobordism from the fixed end to I'll start n prime sub t. So that the given thing on the bottom end is always the same, and then the top thing is, you know, it's diffeomorphic to the original thing, but its description is changing. All right. And okay, and then you can put them all together. Put the W sub t's together as a you know, together n plus 2 dimensional manifold. See, so you've got, so this is my picture I have in my head. Sort of here's, I'm going to take that picture of n cross 0, 1 with some handles attached to it and turn it on its side a little bit. So this is n, this is 0, 1 cross n. I've attached some handles here, but then I cross all of that with I, and in the middle, you know, my handle attaching data wandering all around. So here I have sort of some slice in the middle is cobordism W sub t, and I'm not this. I don't need, well, this whole thing is Z, and I can glue. The point is because I'm not writing more words down. This is a if you like, it's a bundle over the interval 0 to 1 with the same cobordism at one end as it is at the other end. Exactly the same. The cobordism in the middle, they're all diffeomorphic, but its actual description is changing. But these are actually equal to each other because it's the same handle attachment. So you can glue this by the identity, right? And then this builds, you know, really I want to think Z is, I really want to think Z is sort of, which is equals an S1 family cobordisms, or if you like, it's a single cobordism, or it's a cobordism, it's a single n plus 2 dimensional cobordism from S1 cross n at the bottom to not S1 cross n prime, but S1 sort of twisted, some bundle. So the top here is I've got n prime here, and then I've got things diffeomorphic to n prime, then I get n prime again, and I glue this to that. And so when I follow along the top and come back, I get some interesting monodromy. So this is monodromy of the bundle on top. And once you do that, and then this n prime, so emphasize that you fix n prime, it's fixed to some diffeomorphism n, which comes from somewhere. So all of that produces some phi from n to n, which is well defined up to isotopy. And that's a way that, so that's a way that a loop of handle attaching data can produce this automorphism of a manifold. I was being kind of careful about various steps of this and kind of sloppy about other steps, because with practice, the stuff that matters is the stuff you need to say carefully. This is a vague general setup. I'm going to tell you a setting where it works.
So
Yes.
each slice is the
The W, yeah. Just the W. It's just that there's not, the intermediate slices are not canonically diffeomorphic W in a sense, right? And so, right, yeah. So it's sort of it's the opposite of taking integral across something and gluing one end to the other by a diffeomorphism. You're gluing one end to the other by the identity, but the stuff in the middle is changing, right?
So
the
are
description of the
you
stuff in the middle is changing.
are you thinking of this also? I mean, so this description by adding handles you can interpret as Is that what's happening? That you can reinterpret it as Morse function? So this is like a family.
Yeah, this is a family of
Morse
Morse
function?
functions, if you like. I mean, this comes from a surf theoretic perspective. I'm trying to, it's a little hard to be very careful to make that connection. Let me give you a really concrete.
There are intermediate slices where the like horizontal T slices where your singularities aren't just more singularities, right?
Well, you could, I mean, I could even have it Morse for all time. I could even have to, I'm going to give you an example. It's just, so here's a very simple example. I'm going to take,
I guess
I
that
wanna
was my
do-
question. Is this a Morse for all time?
yeah, it could be. It could be or could be. I'm not, the examples I'm going to consider are, okay? I'm going to do a very simple example, a genus 2 surface, right? I'm going to think of n being a genus 1 surface, torus, okay? And then my W is going to be n. So I take a torus, and then I thicken it a little bit, whatever, and then I attach a solid three-dimensional nipple to it. Okay, so this is a if you like, this is a compression body, genus 2 on the top, genus 1 on the bottom. Okay, so take a genus 2 surface, thicken it a little bit, attach a three-dimensional 1 handle there at some point, right? Your attaching data is these 2 points or these 2 discs, right? Okay, now how about I take this foot and I drag it around, and maybe I drag, so here's some intermediate time where it's attached, not there but here, right? So I can take the foot and wander it around and around and around and around until it gets back to where it started. Okay, so the intermediate manifolds, of course, are all diffeomorphic, but I build an interesting bundle. I claim that in the end, if you actually get a diffeomorphism of this.
So how do you, what is confusing is how do you put the HTs together? I guess that's not clear to me.
The
WTs.
if you really want to do it right, I guess you want, well, in this example,
Yeah.
it's okay, right? It's just a single 1 handle. If you like, you could also rewrite it as just attaching round 1 handles in a sense. So if you could say it, I've taken n cross 0, 1 cross S1, and I've attached some, S1 cross handles to it in some interesting way, and the top I get some couplets. But just think about it this way. I started with this picture and I ended with this picture. But in the intermediate stages, this foot dragged around and did interesting things. It came back to where it started. So this foot dragged around some loop. It turns out that the actual diffeomorphism you end up is what's called a point pushing map. It's really 2 parallel copies of Dane twist this way and a Dane twist this way, opposite Dane twist. I think you might have seen that picture a little bit. If you take a handle and just drag it around some loop, drag its foot around some loop on the surface, and come back to where it started, that induces an automorphism of the surface, which is 2 parallel Dane twists, one on one side and one on the other side of the foot along that path. Let me proceed. That was maybe too general, so let me get more specific and come back. So that's a general way you might do things. Here's a specific example of doing that. So let's show a specific example. Which is, let's take that. So now M is going to be S4. Okay, and I'm going to take 2 cases. One is that N, the thing on the bottom, is going to be a connected sum K copies of S2 cross S2. And so how can I connect some of K copies of S2 cross S2, attach some handles, thicken it, make it 5-dimensional, attach some handles to it, and get back to S4. Well, this is, if you think of this as the result of attaching some 5-dimensional 2 handles, you want to attach 5-dimensional 3 handles. Or you can just believe what I said in X. If you attach 2 handles, so we're gonna take this thing, cross 0, 1. And then at this n cross 1, we're going to attach the 5-dimensional handles. I'm going to attach 5-dimensional 3 handles. So those are B3 cross B2s. So they should be attached along S2 cross B2s. So they're attached along two spheres. I'm not going to pay too much attention to how I cross the B2, and you can talk later about why I don't care about framings in this case. Attach two handles along. I'm going to attach K 5-dimensional two handles along the K different two spheres that naturally appear here, which I'll describe three handles. Disjointing of K copies of S2, so that's 3. K copies of S2 cross points. Okay, so inside each S2 cross S2, I pick a point, there's an S2 cross point, and there's one in each summand. And so there they are, and I've attached 3 handles along those. That has an effect. So this is a coordism to n prime, which is a result of surging out those S2s. But in this case, it's actually canonically diffeomorphic. So there's a very canonical handle cancellation that I can just write down coordinates if you like. For a diffeomorphism as a result of surging all those S2s to S4. So what is the attaching data here? It is, so the attaching data alpha is really an embedding of disjointing K S2s into the connected sum of K copies of S2s. And so if I want to produce a loop, if I want to do a loop of this, the simplest way to do this is just take a loop of such embeddings, starting in this point. Okay, so alpha sub t will be really its homotopy class is what matters when we count pi 1 of the space of embeddings of disjoint union of K copies of S2 into the connected sum of K copies of S2. And I'm going to say pi 1 should have a base point. We discussed in my algebra equality class, I'll name this solid based on star, especially when you're talking about reduced maps with stars as well. But there it is. This is star. Base point is an embedding. So I started and ended that, and that's attaching data, and that produces a loop of coordinates from connect sum of S2 cross S2s to something. When you attach exactly along these S2s, you get S4. When you attach along some crazy thing that's isotopic to those S2s, you get something that's diffeomorphic S4, but how it's diffeomorphic S4 is kind of up to you. And that's why in the intermediate stages, you don't have a fixed identification with S4. Okay, so really what you end up getting is you end up getting a map from this thing. You produce a homomorphism actually from this thing to I0 of diff plus. That's the upshot of that construction. But you could do the same thing. Well, you could do with a different number of handles. You could also do the same thing with S1 cross S3s instead. And just for good measure, I'm going to do a single. I can do n equals S1 cross S3, and I'm going to attach 5-dimensional 2 handles now. So 2 handles B2 cross B3 is attached along S1 cross B3. So these can get attached along. Well, initially alpha will be equal to just S1 cross B3. But then this will be alpha 0, which will be alpha 1, and then you'll get a loop alpha sub t will be in pi 1 the embeddings. S1 and S1 plus S3. Now, I could have done K copies of these as well, but you'll see why I don't bother with that. So I also get a map from here to there. And you might imagine these are some pretty specific choices. Why would I focus on these as opposed to all kinds of other things? Let me give just some names to these maps. So let me call this map curly H. I can't remember if this is what I called it last time I looked it up, but curly H sub 3 for 3 handle, superscript K for K handle, H for handle. Okay, so that's a group homomorphism from pi 1 of the embeddings of K copies of S2 into connect sum of K copies of S2 cross S2. I'll give this map H sub 1, 2, 1. 1 because there's only a single copy of S1 cross S3 and a single S1. Okay. And extending, getting this help is elaborating on, I guess. So first of all, the H sub theorem that I proved a while ago is that as k goes to infinity, H3k is surjective. It's not, there's a more precise way to say it in terms of limits of groups, but the rough idea is you can hit any isotopic class of diffeomorphisms of S4 with this construction if you let yourself use lots and lots of two spheres. Okay? And then, but the other part is that so notice that there's embeddings of disjoint union KS2s into S2 cross S2s. What about this S2 lands in a point, right? So this may seem a very specific thing, but I'll just tell you if the image, I'm going to be a little sloppy, the image of I1 of the embeddings of disjoint K S2s into connexon K S2 cross D2s. So I'm thinking of S2 cross D2 sitting inside S2 cross S2 in the obvious way, right? And so if what I'm saying is, suppose I have a loop of two spheres that happens to remain, basically to avoid S2 cross points for other points, right? So it happens to remain these S2 cross D2s. That's maybe a very special case, but it's something worth considering. So this is not technically this space maps into that space, shows an induced map on pi1, and I can consider that pi1, and I can then produce pi0 plus S4 as well. So the image of this in here, pi0 is actually equal to the image, is actually equal to 1 of. In other words, I can replace a bazillion S2s with a single loop of S1s in S1 cross S3 with the same data, as long as I'm able to avoid wrapping all the way around the second S2. Okay. So that, and then this is not like, both of these are a kind of sort of cheap usage of pre-existing surf theory written in Hatcher and Wagner and other. There's a better proof of this now that just appeals directly to work of Craig and never mind. There exist better proofs by people who know this material better in some sense. I want to talk about this group here. Okay, so now, why might this even help you understand this? Well, for example, if you knew that these groups are all, let's suppose you knew these groups are all trivial, you'd be great, right? Oh yeah, this becomes an isomorphism. This K is large enough, so if these groups are all trivial, that's nice. You know, so what do you know about any of these groups? The one thing that's known, so theorem 3 to 5 to I is that this pi1, I'm going to say pi1 of abbreviate pi1 of S1s into S1 cross S3 is a z to the infinity. Do they still say that exactly in their latest paper? I know they've adjusted things.
Yeah, that's still.
I mean, that's still, they've adjusted various things, but so what that meant up to now is that I kind of understand. I mean, still remember the whole thing we're looking at could be true, but there was a z to the infinity mapping onto some part of it. For those who thought about surf theory at all, another way to think about this, these are canceling 2-3 or canceling 1-2 pairs and families of them. And so this is sort of these are sort of very, one wish in higher dimensions, one can often reduce everything in this case. It's a lower dimensional case, right? In dimension 4, there's some structure. Yes.
Is the z to the infinity, is it like the direct limit is u to the k or is it uncountable?
Oh, it has, what do I mean by that? It, they give a accountable list. It's free abelian, and they give a countable list of generators. Does that answer your question? Yeah.
Is it possible to see?
Well, yeah, maybe I'll show you what some of these loops are. Yeah, they're nice. They're cool to talk about. Well, so that means there's a z to the infinity mapping onto this thing that we understand, right? Well, so I used to think that was all I knew about it, but the latest theorem, myself, Hartman, is that this H2, 1, 5, 1, 1s and 2, 3, collapses hugely, and it's either, I'm just saying, it has those two elements. In other words, it's either the trivial group or it's and so all that z to the infinity collapses, and that's sort of, you know, so sort of at least maybe like a model for what you might like to do in more other. So I'm going to give you the skeletal outline of how we show this. Any questions? Hi, Nick.
Can I ask a question?
Yes.
So you have this statement, this theorem that image of pi1 of the embeddings is the same H2 of 1 of pi1 of embeddings of S1. And this is for any K?
Yes, for any K. So the idea is like, they, you know, so if you've ever, you know, this won't mean much to some people, but you have sort of a surf graphics that have nested. In surf theory, these things correspond to nested families of canceling 2-3 pairs, 5-dimensional 2-3 handle pairs. And then this is like 2-3, 2-3, and then there are various surf moves that work in higher dimensions that'll let you play around, trade, you know, higher index critical points for lower index critical points, merge things, all kinds of things that work in higher dimensions that are fiddly in dimension 4. But it's saying that under right conditions, you can translate this. First, you can translate them all into 1-2 pairs. And then once they're 1-2 pairs, there's some little surf moves. You can like put a little swallowtail, merge that swallowtail in there, and blah, 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 and eventually get it down to a single index 1-2 pair. That's just the flavor of that kind of stuff.
Okay, I understand. So now I don't understand the theorem up there. I'm totally confused. This image, the first image, it's image under H3K?
Oh, yeah, the image under H3K, yes. The H3K of. Now, that should be a little bit less sloppy. So remember, the domain of H3K was pi1 of the embeddings of S2s and S2 cross S2s, right? Now I've got S2s and S2 cross D2s. So really I should assert H3K of I star of, right? Because this space of embeddings of S2s into S2 cross D2s is a subspace of the space of embeddings of S2s into S2 cross S2s. And then I've got reduced map on pi1, and then I've got H3K. Yes.
And S1, S1, and S1, those are the same.
Yeah. Just this is my sloppy abbreviation for that and this one.
And smooth.
Smooth that. Everything's smooth category.
Okay. Now I understand. I didn't see the D2 versus S2.
Yeah. That's the important thing. And so it's like it just, you know, well, fun thing to think about. Like we just don't have a lot of examples. tables here to really think about the difference between the S2 and the D2. And I made a mistake early on in this, and I thought I didn't need this D2. I thought I could do S2 cross S2 at one point, and then that was a much bigger thing. But I don't know, it may be true, but I don't. All right, so what's this? Let me give the outline of the proof. So once again, we've got just so H2. I'm just going to call it H now. I'm going to drop the subscripts. It's the handle data attaching that thing, and it's going to go from pi1. I'm not going to talk about S2s anymore. I'm going to work entirely with embeddings of S1s into S1 cross S3. So this is my abbreviation for embeddings of S1 into S1 cross P3 based at the embedding S1 cross points. Okay. And that goes to I0. Oh, you know, and then the other thing, like why is such a thing? Why is such a translation useful, even in the S2 case? Well, you know, how do you describe a diffeomorphism of forces? Well, I mean, just to get you, you know, you might think, oh, well, surfaces. I know how to describe diffeomorphisms. Surfaces just gain twists, right? Well, when you do that, when you say cut on these circles, twist, and so on, you're sort of implicitly extending across disks in the only way you could do it. Well, we don't know anything about. We don't even know. I mean, it's sort of the same thing. We don't know whether any two diffeomorphisms of the four-ball that are the identity on the boundary are isomorphic. So you know, if you have a problem, how do you describe things on the whole ball? You basically have to describe things at every point in some sense. So one hopes for some more combinatorial way to get at this stuff. And so ideally, maybe embeddings and circles and spaces, even loops of that, are better than just single elements. Okay. So the other thing that I did in the paper was I showed that Gavai and Budney give generators, which I have time, I'll try to draw. And so the Gavai, Budney Gavai, they give various versions of it. We'll call them alpha of I. I'll use sub T to indicate that. So this is alpha I is a particular embedding. Alpha I sub 0 is a particular embedding. This is mine. So I is the index in their countable list of generators. The sub T is the loop parameter, and then on top of this bracket is on the class here, and that maps to particular. So I can describe these diffeomorphisms in a different way over here. What I call tau sub I. This is twist. And I'm going to describe this long Montesinos twin. So very many things to be described here. Montesinos twin, W of I, which is R of I. Okay, so all right. So what is a Montesinos twin? Montesinos studied these. This is a pair of so these are both R of I. So Montesinos twin in general. W equals R comma S. R and S are embeddings of S2 into S4. So the Montesinos twin is a pair of embeddings of two sphere into S4, which meet transversely at 2 points. I'll just draw like that. That's what a Montesinos twin is. A pair of two spheres in S4 meeting transversely to a pair of points. It necessarily comes with opposite sign because it's S4. So I will tell you later how such a thing describes in a self-diffeomorphism of S4. And there's a sort of very nice way to go from this loop of S1s and S1 cross S3 to this Montesinos twin. And so, but for the moment, just think that's a black box. You could, I give a list of Montesinos twins. It turns out that the first sphere in each twin is the one that changes as I varies. The second sphere is the same in all of them. Okay, and then there's a recipe to turn such a thing into an automorphism of S4. And so I'm just trying to give the formal outline for the proof. Okay. Then, in general, if so this is step one. This is what this was also I think, general paper, all this stuff up here. Okay, the new stuff is, so first observation is to know that if, so suppose I take, these are oriented two-spirit, by the way. That does work. So if I have W, which is a quantity twin RS, I can do something called W bar, which is just, don't change the orientations on the spheres, just label them back, you know, switch their label. It's an ordered pair of spheres. This gives there's a twist along this one and a twist along this one. And the claim is that the twist along W inverse is the twist along W bar. So just by switching the two factors, you do the inverse of that. Okay, that's a fact. Next fact is that's not hard to prove. Okay. All right, so now, next thing is we construct three for each W of I bar. So when you take this WI, which I produce in my paper, you take that and just flip the two factors, right? There you construct a loop of alpha of I sub T bar of homotopy class in I1 heading to S1 S3 in a certain way, and such that H of this alpha of I bar sub T equals this W. This is sort of there's a geometric way to translate between loops of embeddings of S1 and S3, in S1 plus S3, and these Montesinos twins. And if you flip the two factors of Montesinos twin, there's a natural way to reverse engineer that thing and get this other loop alpha I bar. So there's a sort of a natural loop of S1s and S3 that represents the inverse of the loop. I mean, there's also, see, there's two ways I could get. Sorry, there should be a tau sub W by bar. Of course, knowing that tau sub W I bar is tau sub W of I inverse, of course, I could just run the loop backwards, because that would be just doing the inverse in I1, right? But I could also just produce this other thing more geometrically. So don't, just produce somehow, and it has this property. It's a particular loop with that property. Is not actually alpha of I sub T run backwards. Just some other loop of embeddings of X1, X3. And then, okay, so this is the step 3 is in pi1 of S1's index 1 by S3. It turns out that this loop alpha of I bar is actually equal to plus or minus I alpha of 1. Let's see, first of all, I'm using additive notation because goodbye, but show that these are abelian groups. And interestingly enough, pi0 plus of S4 is actually also abelian. You can figure that out directly with this constant. But anyway, and then this plus or minus can turn out not to matter because I'm sure we're going to show that everything's important too anyway. So it's mostly just plus or minus, it's just being too lazy to be careful because it didn't matter. So let me see if I'll have a picture for you in a minute, but let me finish it. So this is what Daniel, this is the, I said Daniel did the calculation for me after the paper, and that's what he was able to figure out, and that was crucial. And he did a calculation by just calculating some variance they had. I'm still not entirely clear whether we can just really see it explicitly, that homotopy, but it's a homotopy between two loops, right? Two loops of embeddings of S1s. Okay. And finally, step 4 you prove that actually W of 1, which is given our, well, I'll just say W of 1 is this is a pair of two spheres. And it's actually isotopic. So there's an isotopy that reverses the two factors. So if you put everything together on these two boards, you should be able to get the theorem. So let's see, maybe I can just, maybe I'll kind of, let me maybe make a little picture here. So here's I1, S3. Here's the Levy and devise generators. So there's alpha of 1 sub T, alpha of 2 sub T, alpha of 3 sub T. And each of those really generates like a whole Z, right? This is my picture of Z being infinity. So there's a Z, there's a Z, there's a Z, right? I mean, really, they should be intersecting at 0 or something, right? But these are these generators, right? 4 sub T. Now we look at where each of these go in I0 of this plus of S4. Okay, and these go to twists along W1, twist along W2, twist along W3, etc. Now we look at their inverses. Okay. These are their inverses, etc. Now we reverse engineer this process, and we notice that all of these things land here, just in that Z. I mean, this reverse engineering process is not a conformance. It's just finding, it's just a list. It's finding something that maps to that thing, right? So we take these, get them back here, they all ended with this Z factor. And then we discovered that this thing equaled its own inverse. And that's what this whole Z factor maps to. So therefore everything works. That's the outline. So then let's see how much time is left to draw pictures. I think everything formal is there, and so we just need to draw pictures now of what these different loops are and so forth. So it's just a weird, I mean, there may be a clean way to sort of back and forth. It's not some weird back and forth. So let's see what pictures I want to do first. Well, let me tell you what a twist along one Stevens twin is. One Stevens twin. So here's the crucial thing. Draw it schematically. This is R, and this is S. These are supposed to be two spheres in S4. So the first claim is that the boundary of the Jupiter neighborhood of W Jupiter neighborhood of W. The claim is that's its frequency. It's sort of naturally, canonically parameterized. So there's an S1 sub L cross S1 sub R. So how do these three factor? I mean, you have to believe this or play around with it to convince yourself. It's kind of cool to try to see this. So the S1 sub L is called L for longitude. It's the factor that's homologically trivial in the column. So this is S1 sub L schematically. It bounds. Then S1 sub R is the boundary of meridian disk to R. So this is S1 sub R, and S1 sub S is the boundary of meridian disk. If you were looking at this two-dimensional picture as a cartoon, then think of each of these as S0s. And what you see there, 4 circles, is S1 cross S0 cross S0. S0 cross S0 being 4 points. So that's, if you like, this is the two-dimensional neighborhood of that. And a lot of things work by analogy. So. Furthermore, if you adopt all the right conventions, these are oriented, this is oriented, everything's oriented. So a neighborhood of the boundary of the neighborhood of W is -1, and this, and then this is an annulus. And then so you adopt some convention, so everything's oriented a particular way, and then you do a Dane twist here, and you do the identity here. Product of those is called the Dane twist along that line. Okay. Yes.
W is just the point.
Point you the union of two. How might, let me just say some words about saying anything. How might such a thing be related to a loop of circles in S1 plus S3? Well, very special property of all of the Montesinos twins we consider is that both R and S are actually unknotted two spheres. Okay, so you can surger along either one of them. And if you surger along in S2, it turns S4 into S1 cross S3. And it turns the other one into a T2, a torus. So that's really what's going on. Is you surge along S, and R becomes a T2 in S1 cross S3, and that T2 is a family of S1s. And that family of S1s is your loop of S1 cross S3. So that's the geometric back and forth. You surge along this, and you get one loop. You flip them, you surge along the other one, you get a different loop of S1s, S1 plus S3. And that's the geometry one. Okay. Let me draw a picture at least of what some of these loops of spheres look like, and then I'll stop. So here's what W3, here's what W3 looks like. I've drawn various pictures in my life. I like to draw pictures that involve a snake swallowing its own tail, but here's a actually better picture. That's my favorite picture, but it's not as mathematically useful as this one. So what do I mean by this picture? So the red, the blue, and the green are equators of two spheres. And this is the T equals 0 slice. You move forwards and backwards, blue and green shrink to points. Okay, so each of those is an unknotted two sphere. This white arc goes and connects a point on one to a point on the other. How do you get a Montesinos twin out of that? You do what's called a finger move. You put your finger along one of these arcs all the way around until it comes here, and then just push it right across, and you'll pick up 2 points of intersection. Okay, but you could do the finger move the other way. And then I like this picture because it sort of allows you. So basically, you take this and you push, 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 push until it hits the other two sphere. And when you push a finger of one two sphere across another two sphere in 4 dimensions, you'll pick up 2 points of intersection. And ask that if you want. Okay, and so this is a way to make a pair of two spheres intersecting twice like this. That can be turned into, so here's the, I'm just going to leave it to your imagination. I'm going to produce out of this. I'm going to tell you what you get if you surge along. I'm going to draw 2 different pictures of a torus in S1 cross S3, and then I'll stop. And one of them comes from surging along the blue, and one comes from surging along the red from the green. I'll see if I
Can you excuse me, Dave, it's impossible to see the colors through Zoom.
Oh, okay. So S and R. Okay, green, blue. Okay, and I should have chosen better colors for remote viewing. So here's one picture. tell you what this picture means in a minute. Something like that. Okay, so this is the same thing. So this is a picture in S1 cross S3. So this direction is S3, which is really, and this direction is S1. This is a torus, which it mostly is sort of, most of its body is straight up and down, runs across the S1 direction, except there's this little finger that comes out, wraps around, and then clasps in some way. So what's going on here, don't worry too much about it, because basically it's puncturing twice in this slice. You see it self-intersection, but really it's sort of like it's a four-dimensional version of an over-under. Okay, so it's going over and under in the x direction. Don't worry too much about the details. This is and then the loop of circles you get starts with this circle here, and then moves around the torus. So eventually the circle sort of develops an elongated piece that spins all the way around. It doesn't do much until it comes back to right here. So I'm way out of time. So let me just end with the other picture that you get when you flip the two components. You get something that's suspiciously similar, but not quite. And it looks like here, there's going to be a big fat head. And instead of, now you're going to line up 6 of these holes here. This thing's going to come through, come around, and then come through again. I'm sorry, I'm being very sloppy. I think you get the picture though, and come around and go up. So it goes around this way once, but it cuts through the head of this snake 3 times instead of going around here 3 times and through the head of the snake once. Okay. This is Gabai's alpha, Budgie Gabai's alpha 3 sub t. This is our alpha 3 sub t bar, which then Dan was able to show is isotopic or homotopic of a loop to 3 times alpha 1 sub t plus or minus, where alpha of 1 is where you just go around once. Okay. That's basically it. You know, in a nutshell, of course, there's lots of details, but other stuff.
So, is this torus even embedded?
This torus is embedded, yes. This torus is embedded, so it's immersed in this 3-dimensional picture. But what's happening here, you've got this, I mean, so really it's coming, so I mean, what's that's slightly better picture. You've got something like this. Here. Okay. And so this, in 3 dimensions, you have 2 circles of intersection. But then you push that disk, say, forwards or backwards in time. I think you push them forward, backwards, or push, or you can, that's what I provide an over under operation for dimensions. So it's immersed, it's embedded.
That's even stronger than
You're absolutely right. That's sort of an amazing side effect of, I don't know what consequence really, except that you can work with them very geometrically. And side effect of Budgie Gabai's like explicit list of generators for these embeddings is that they all can be realized by embedded torus. I don't know. I was also asked them if they knew with a priori reason that would be true. And dude, if you have a loop of embeddings of S1s, then for different times, like time 1/2 embedding might crash through the time 0 embedding. So you should not expect a loop of embeddings of S1s to in general give you an embedded S1 cross S1. You just know that each S1 cross point is embedded. And so this is where this point is that's a bit surprising. Oh, the final, so I know that the whole thing, I mean, I didn't, yeah. So this, we show that this particular subgroup is 0, or it has at most 2 elements, right? The Z2 maps onto it. It would be great to know if it was trivial or not. I mean, actually, one thing I thought is we can do it in R4 as well, of course. Can we show it's symplectic, and then it'll be trivial, right? Preserve the symplectic, right? If I could show this automorphism of R4, preserve the symplectic from the 4-ball. Anyway, that's not a thing. I don't know. Like I have no idea if you really. It's really hard to explicitly isotope things around to be trivial.
How did
But you know,
know that you're generating something?
they have an invariant, which is coming from embedding calculus and some configuration spaces. And it doesn't. I don't think it works. It's like they put embedding calculus. It likes certain codimensions and certain dimensions, and it's kind of like as close as they pushed it. I think they pushed it as much as you can. Like they got right to the border of when embedding calculus tells you anything. So I don't think they can say anything about 2 dimensions inside loop pi 1 of S2s and S2 cross S2s. I don't think they can say anything about that. This is the paper though that has the knotted 3 balls. So in S4. That's where they use this calculation just in order to get interesting embeddings of the 3-ball S1 cross.
Of 3-ball in?
Well, in S4 or in S1 cross B3, if you want to think of, so their thing is you've got, when Gabai first announced this result, nobody understood it. It sounds stupid. It says that there exists knotted 3 balls inside S4. Well, anyone knows that any ball is isotopy to any other ball because you can make them just shrink them to very, very small ball points. And so, but the point, what it really means is fix the standard S2, fix the bell bound. So fix the standard S2 and S4, and look at all the balls that are bounded by that, that are bounded by those 2. Then there exist balls that are not, which is very different from dimension 2, where dimension 3, where disk, the unknot bounds disk. Any 2 disks bound by but any other questions?
Just to confirm, for the 3-sphere, it's known that the diffeomorphism has the neutral type of tracks.
Yes, absolutely. So yeah, so yeah, I mean, maybe the real background to all of this is that yes, very little is known about pi 0 diff plus of S4, but the amazing fact was due to Watanabe is that higher homotopy groups of diff plus of S4, which are not the same as higher homotopy groups of S5. So that's disproved the Smale conjecture. The Smale conjecture would be that. So, you think of this N sphere, that's nice round object in Rn plus 1, so you can act on it by SO plus 1, right? So you might say, well, maybe every orientation preserving diffeomorphism of the N sphere can be homotop to a rigid rotation, and in families of them can be homotop to rigid families of rigid rotations. That's saying that diff plus of Sn is homotopy equivalent to SO n plus 1. That was the Smale conjecture, and Watanabe is disproved that. But using higher homotopy, not higher, and using configuration space stuff.
Can I ask a Steve question?
Yeah.
So do you have a reason to believe that to be true in dimension 4, but not high, possibly not higher dimensions?
Sorry, do I have a reason to believe what about dimension 4?
To believe that Smale conjecture is true in dimension 4.
Oh, well, the Smale conjecture is now not true in dimension 4.
Okay, yeah.
But it's not true for higher homotopy reasons.
Right, yeah.
So what I'm saying is I still have no, and to higher dimensions, I to be honest, I'm going to get confused if I say something about higher But what I've focused on is like, just, what's this stupid pi zero, right?
Oh, just, okay.
I only, I sort of like to, block everything out of my mind. I just want to understand pi zero,
Oh, just pi 0. Okay.
which is a bit narrow-minded, right?
Yeah. Okay.
But I want to understand pi zero of div plus by understanding pi one of other things.
I see.
So I just.
Like a point pushing map thing.
Yeah.
Can you repeat
Yeah,
the
this-
question?
So wait, was I think asking like, how is this related to like point pushing map? So if you have a loop of embedding of objects, then you can, by isotopy extension, you have a loop of embeddings as isotopy of some submanifold. Isotopy extension will then give you a one-parameter family of diffeomorphisms of the manifold that implements that loop of embeddings. However, it's important to remember the time one diffeomorphism will not be the identity. But the time one diffeomorphism will be isotopic to the identity. So it doesn't, right on the nose, that does not just take an object and move it around in your space, does not give you a non-trivial element of pi 0 plus.
Yeah, but then.
But what you do is you do this point pushing and then you search it. So that's the typical thing, like you work in some, it sort of is the same thing. I mean, the translation between these one parameter families of circles and these Montesinos twins really goes through point pushing. Okay, but you move something around in some other manifold and then you search your way so that the thing that would let you isotope it back to the identity is no longer there. And you're left with something interesting.
I think there are a whole bunch of the equivalent things about the three-sphere like this.
You're talking about the appendix of
The
Hatcher's.
tracer patch.
Yeah, this is my favorite project for some graduate student reading group, is to read the appendix of Hatcher's paper on the snail detector, in which there are 11 different equivalent, which I've never read. I've opened it, I'm like, wow, someone should read that experience. Do you understand it?
No, are there a bunch of things like that that are now known to be false?
Oh, that's a good question. I don't know. Yeah, so Hatcher proved the snail conjecture in dimension 3. And it was a big deal. And then his paper gives lots of equivalent things like about pi 1 and embeddings knots and all kinds of interesting different homotopy groups of this and that's being trivial homotopy equivalent to each other. I just feel like it's rich, that appendix. But and I don't know, but that'd be kind of a nice project to see what translates to other countries. I mean, probably again, sort of thing probably experts know, like embedding calculus people, but all right. Who's on next week, by the way? Remember? We have a speaker. We have a real speaker next week, right?
It's Gage.
Oh, yeah, that's right. Yes.